talk about some properties of groups. That means there are some general properties that every group will follow. Every group will follow. So first thing is, we have seen that every group has an identity. So the question is whether there are more than one identity. Okay, so that is we are going to ask, is there more than one identity in G? Okay, so this can be answered by a theorem. Uniqueness of identity. Okay, so what is it tells you? So this tells you that in a group G there is only one identity element. Okay, let's see a quick proof of it. So for the sake of a contradiction, we assume there are two identities. So let it be E and E dash. Okay, so they are in G. Okay, so we know the identity has to follow two rules. That means for every A in G, A E equal to A is equal to EA. So let it be 1. And similarly, we have E dash is also an identity, so that also has to follow the identity axiom. So it is E dash equal to A equal to E dash A. So let it be the equation number 2. Now you can see in 1 it is for every A in G. So E and E dash now in G. So let's put A is equal to E dash, right? Then what happens? This implies A E dash E is equal to E dash is equal to E E dash. Okay, let's the equation number 3. Now in 2, let's put A is equal to E. Then what happens? That becomes E E dash equal to E equal to E dash E. So let it be 4. So 1 and 4 I want to concentrate on this part. So let E E dash equal to E dash. Similarly here also E E dash is equal to E. So what I can do is from 3 and 4, this implies that the right hand sides, they are equal. So that means E dash is equal to both. That means E is equal to E dash. So if you assume two identities are there, then they must be equal. Or what you can say is there is only one. There is only one identity inside G. Okay. So that's the first theorem. Next we want to do a very natural property we observed in real numbers. That means if you can see, if 2 plus 3 equal to 2 plus 4, then naturally we can cancel the 2 both sides. We get actually it is not true anyway. We should write like we give some values. So if a plus 3 equal to b plus 3, then we can cancel b from both 3 from both sides, and we can assume that a must be equal to b. Similarly, if 3 plus a equal to 3 plus b, here also you can cancel from left, we can conclude it to b, right? So is it possible in a group? The answer is yes. So let's look at a theorem. This is called cancellation law. Cancellation law. So what it is tells you, in a group G, the right and left cancellation laws hold. That is, what is the meaning? BA equal to CA implies B equal to C. Similarly, AB equal to AC, that also implies B equal to C. So let's see a quick proof of it. For that, let's assume E is the identity in G, and A dash is the inverse of A in G. Now let's take BA equal to CA. Then you can operate A dash the right side of the equation. So what you get is, right, now A dash being the inverse of A, you can make A dash, you can make it B, E. So C is E. Now you can see that anything multiplied by B, E is same number. So here it is. So we are done. So from BA equal to CA implies B equal to C. We cancelled A using the property of inverse and identity. Similarly, you can do this also. AB equal to AC. This implies you multiply A dash with left side. So this will become EB equal to EC. So this is B equal to C again. So cancellation laws hold in groups. Okay, now we are ready to prove whether we found that for every A in G there is a B in G, that B is the inverse of A. Okay, so what our problem is, do A have more than one inverse? Or is inverse unique? Okay, so let's answer this. So theorem 3, uniqueness of inverses, right? Okay, so what it tells you, that for each element A in the group G, there is a unique element B in G such that AB equal to BA equal to E. That means inverse is unique. So that B is actually the inverse, right? So how do you prove it? So for that we assume that A has B and C both are inverses of A. So you know that of B being inverse, we can write AB is equal to E. Similarly, C being inverse, we can write AC equal to E. So their right sides are equal, so we can write AB equal to AC. Then by theorem 2 or cancellation law, we already proved it. Cancellation law, we can cancel A both sides. Cancel A left side of equation, left side. So what do we get? We get B equal to C. So if there are two inverses B and C, they must be equal. That is, there is only one inverse. So only one inverse. Next thing is, how do you find the inverse of a product in a group? How do we find inverse of a product of a group? That means if AB in G, what is AB whole inverse? Okay, so let it be theorem 4. We call it socks shoes property. I will explain why it is so. So what is it? This tells you that for group elements, A and B, AB inverse is equal to B inverse A inverse. So it can be proven easily from cancellation law. You know that AB all inverse times AB, right? So let's move it a little here. So AB into AB inverse, surely it is E. Now let's work out AB into B inverse A inverse. What happens to this? So let it be, this is equation 1. Now we work out this particular product. So what happens is A inverse, and we know by identity B inverse equal to E, right? And again we will make it A inverse, so this is also becomes E. So equation number 2. So equation number 1 and 2, the right sides are equal, so we can equate the left sides, right? So this is equal to AB B inverse A inverse. Now we can cancel AB from left. So if you cancel AB from both sides of equation from the left, what you get? AB inverse is nothing but B inverse A inverse. Okay. So why it is called Shocks property? Because while wearing the shoe, first you put the step is like that. First step is put socks, right? Socks. Second step is put shoes. So like socks is A, shoes is B, right? Okay, now how to unwear it? To unwear, what the first step? Remove shoes, that is opposite of B, inverse, remove shoes. Second thing is remove socks, so A inverse. So that's why it is called a Stokes property. So it's an inverse operation. You do AB, but to remove AB you have to do B inverse, A inverse. Okay, these are the some general properties. Okay, so next we try to define what is mean by a subgroup.